So how does this thing work? Oh, nice. Okay, so I'm guessing I'm live. Gonna wait till my picture shows up. Okay, there we go. Okay, let's get some, put my face here. And I think I'll go on YouTube, find the, okay. Ozzy Phantom. Tutorials. Okay. Like, oh, like, okay.
I think it's like someone that has a harder time with autism, like a good doctor.
Okay.
You know what I mean?
Yes.
Are you okay?
Yes.
Are you working on your?
Yes.
What your assignments are?
Yes.
Okay. So the article just states, because I gotta talk to Pauline, I don't want to ignore her.
Okay.
So it just states like sometimes he didn't know what to say.
Okay. Okay. I don't know why it didn't show up, and yeah, it looks like I'm spelling his name. What? Yeah, I know. Okay.
Elements of a snare.
Okay, so here's the oh, his YouTube name is Ozzy Fanto. There's no M at the end of, like, what's, okay, let's get the let's check my own live stream to see if it's anybody's. Okay, let's get the okay, put the volume down my own live stream. Okay. How many people are watching? Mom, I'm busy right now, okay? Okay, I need to, wait, let's go to the studio. How do I get into studio mode? Okay, it says one. You know, I don't know how to get back to the studio mode thing. Wait, I should. Okay. I'm going to get some people on Discord to know that I'm live streaming right now. Open up Discord. What the heck? Live. Going to review Ozzy Phantom's SNES tutorial. Okay. Okay. Okay, so I think I'm ready to start this. I think I'll okay. Okay. I'm starting the Phantom review. If you want to see the video from the beginning, you can go back on the live stream. Okay, so here it comes. I think I'll put the volume. My computer is going slow today. Let's move it back to 50%. Dang it. Go.
SNES engine. This video has two parts. Elements of a SNES engine. This video has two parts. The first part I'm going to explain the V-blank and the CRT cycle. In the second part I'm going to talk about the three main loop options of the SNES, with a deep dive into the most common one and explain all the traps. So even if you already know about V-blank and understand how it works, then skip to the next part. Even if you already have a working loop, I highly recommend you watch my walkthrough, as there are a lot of traps and I have not seen a tutorial cover them, so you'll probably still gain some info. On to the first part. The first thing you need to understand is how the PPU and V-blank rule the roost. I've seen a lot of newcomers come in without understanding this. You may think the CPU is in charge, so you set up your frame and then you tell the PPU to draw it. This is not the case. There is no frame buffer as in a bitmap-based computer, but the frame is actively drawn live. This means the PPU draws what it has when it needs to. So every 60th or 50th, depending if you are NTSC or PAL-based, the frame starts drawing.
Like, by the way, I want to say, I like how this guy brings it up that a lot of newcomers believe that the
and then you tell the PPU to draw it. This is not the case. There is no. A lot of newcomers come in without understanding this. You may think the CPU is in charge, so you set up your frame and then you tell the PPU to draw it. This is not the case. There is no frame buffer as in a bitmap-based computer, but the frame is actively drawn live.
Yeah, this is something that I like. It always annoys me whenever I see like people on SuperMarioWorldCentral.net, like there's this like to me, there's like this like misconception that using big sprites causes more slowdown than smaller sprites. I mean, there's there are a few different sprite size modes. There's like the limitations are that there's like 4 available sprite sizes, like 8x8, 16x16, 32x32, and 64x64, and there is a limitation that you have to pick only 2 of the 4 sizes to use at one time. So if you're using like only 8x8 and 16x16 sprites, you need to use like a bunch of like build larger sprites out of the smaller ones. But when it comes to what was I going to say? Yeah, but a 16x16 sprite does not take more CPU power than an 8x8 sprite, and there's also like modes where you could get, like bigger sprites. Like you could choose like 16x6, having sprites that are 16x16 and 32x32 sprites, and like it's it doesn't take it actually using 16x16 and 32x32 actually takes less time than 8x8 and 16x16, because you wouldn't have to build the big sprites out of smaller sprites stuff. But it's the only time that making a bigger sprite takes more CPU power is when you're building a big sprite out of smaller ones. I just wanted to make that clear,
This
because there's
means
a lot of
the CPU
confusion
draws
on
what it
websites
has
like
when
Super Mario World Central about
it
that.
needs to.
Let's
So
see.
every 60th or 50th, depending if you are NTSC or PAL based, the
nobody's-
frame starts drawing.
Oh, two watching.
If you are ready or not, it will start to draw, and then a 60th or 50th later, it will start again. You can't slow it down, you can't pause it, you can't control it. Well, you can turn it off. Every 60th or 50th, it happens. You get a V blank, and then the screen will start to draw. And you have to be ready, or you drop it. If you are not from the CRT era, I highly recommend you watch the slow-mo guys video, link down below in the description, so you can see
Hey,
it
that's
happen.
the lady from the Big Bang
The
Theory.
PPU marches down the screen line by line at a constant, unwavering rate. The frame starts at the top, draws a line, then retreats back to the left side, then the next line, retreats back, next line. It will do this for 224 lines. I'm assuming 224 line mode for all of
Might
this.
as well look at this person.
And then it slowly makes its way back up to the top. And this takes the same amount of time it would take to draw 38 lines. On a PAL machine, the screen actually has more lines, but the SNES doesn't show them and treats them as if the beam is going back up the screen. Only it keeps on drawing nothing for 50 lines, then slowly retreats for 38 lines. The dotted lines form what is known as blanking, i.e. the raster beam is turned off. The right to left are H blank, the bottom to top is V blank. To recap, on NTSC 224 lines mode, you have 224 lines of active screen followed by 38 lines worth of V blank time in which to make your updates. On PAL 224 lines mode, you have 224 lines of active screen followed by 88 lines worth of V blank. Thus, on an NTSC SNES, you can DMA up to 5.9K per V blank. On a PAL SNES, up to 14K per V blank. These limits will haunt you, I promise.
I think it could do me. Yeah, that's something that I've questioned. Wait, where's the my computer's being so slow. Come on. Come on. Why is my computer being so dang slow? Okay, I guess I can't get the... I can't... Oh, fuck. No, now I can't get back on the... My mom is gonna barge into my bedroom like any minute, like force me to eat food, and then claim that I asked for it despite not asking for it. Then ask some like embarrassing question about, well, basically, then maybe ask if I'm masturbating, because she always does that. Come on. There we go. I don't know what... my computer's being so slow. My computer was probably programmed by one of those people at Capcom. Oh my god. Taking this thing so dang... People are probably... I don't know what that's supposed to mean. Yeah, my computer's being slow.
Now, to understand the implications of this, we need to look at the parts of the SNES. We have the 5A22 CPU.
So what I was going to say is that I got when I did the calculation earlier, I got like a little bit over 6K, and I actually found out that this is true if you're doing 37 lines. Apparently, the first line, if you do it the way I do it, and I usually like turn a force blank off like during V blank time. I mean, putting forced blank on during V blank time. Like I'm allowed to get 6K like under within V blank. It's just that if you turn the thing on during scan line 0, it just doesn't show the sprites on the first scan line, which I think is okay because I never noticed it. So
we need to look at the parts of the SNES. We have the 5A22 CPU, 128K of work RAM, the PPU, 64K of video RAM, color graphics.
Yes.
Are you okay?
Yes.
You sound agitated.
Oh boy. Yeah. Oh yeah, I was gonna say earlier
Now to understand
like earlier with this DMA bandwidth thing, like it reminds me of like some like back in like I think like around 2013 I was trying to do like a port of Gunstar Heroes, which I eventually got bored of, and I decided to make like my own like original game. That's something like I was posting stuff on like NintendoAge.com about this has always been like one of the most annoying limitations of the Super Nintendo. I was talking about like bandwidth and like animation frames, and what's frustrating is that a lot of the people were on Sega16.com like had a link to my thread on NintendoAge.com, and a lot of people were just like misconstruing what I was saying about DMA bandwidth as in CPU bus bandwidth. Which is stupid because like I mean I've made it clear that the CPU like cartridge bus bandwidth is not the problem. It's the DMA bandwidth that's I mean like with the CPU, in order to solve the CPU problem, you just have to optimize it more there. That's it.
Understand
But
the implications of
with
this.
this
We need
DMA
to look
thing,
at the
you just have
parts
to program around this limitation.
of the SNES. We have the 5A22 CPU, 128K of work RAM, the PPU, 64K of video RAM, color graphics RAM, and object attribute memory. The SBC 700 with 64K of audio RAM. The CPU has full access to WRAM, the PPU, and SBC 700 at all times. However, access to VRAM, CGRAM, and OAM is restricted to blanking periods only. The SNES won't warn you about the gates to said RAM closing. It will just throw all your data against the wall and not say anything. This means you don't update the CPU state live. During the active frame, you generate all of your changes and modifications to the PPU and VRAM state. Then, when VBlank happens, push all your updates to the PPU and VRAM. Typically, you will just mirror OAM, as you'll probably want to update most of it each frame. CGRAM depends on what you are doing, but you are more likely to want to just push a new value here and there rather than all 512 bytes. But for simplicity, you might just mirror the lot and send all of it when needed. VRAM updates such as new screen map data, new screen frames, etc. you will want to do as a stack buffer that you pile up all of your changes, and then in VBlank you then walk through them and make your sparse updates. But how do you sync your updates with VBlank? The SNES gives you three main options. The NMI only. This is the simplest form and, for lack of a better term, classical format. For example, Super Mario Bros. On the NES and a lot of other NES games work this way. The NMI routine, just bit $4.10. You do your VRAM, your ORAM, your CGRAM updates, you scan the pads, you do your game logic, you RTI. The main game loop is just jump main game. It doesn't do anything. This way you only have one thread and everything is synced to the frame.
Well, I want to look at this. Wow, that's like only like 2 and...
While your game runs in one frame, this is perfectly adequate. The SNES offers the inverse of this, the no NMI. Main game, you just WAI, wait for the interrupt, then you bit 4210, do your VRAM, ORAM, CGRAM updates, you scan your pad, you do your game logic.
Hey, by the way, I just want to by the way, I just want to look at something. I thought that every time it goes like it gets the update, I always thought that you have to like, you know, like like fiddle with, you know, like the registers and stuff. Like, wait a second.
While your game...
Wait, is this... Huh. And in my routine... Yeah, I don't get it.
Game runs in one frame, this is perfectly adequate. The SNES offers the inverse of this, the no NMI. Main game, you just WAI.
Oh wait, now.
The SNES offers...
Oh no, now I get. So. Okay, so this is, when it says the NMI routine, I think that this is... Oh wait, never mind. It says, you know, I don't know. I really don't know.
Is the inverse of this, the no NMI. Main game, you just WAI, wait for the interrupt. Then you bit 4210, do your VRAM, ORAM, CGRAM updates, you scan your pad, you do your game logic, and then you jump main game.
Yeah, you know, like, does the 65816 like show up as 8-bit by default? And I don't, I never, I always assume that it just shows up like what it was like previously. Okay, I guess maybe with this, because it's from my computer's...
Basically does the same thing. Just make sure you don't set up any IRQs in this method though. The two-thread system. Here you have the NMI deal with your VRAM updates and pad reading, and the main loop updates the game logic.
Oh wait,
Set up any IRQs in this method though.
Oh wait, this is the no.
The two-thread system.
Okay.
Here you have the NMI deal with your VRAM updates and pad reading.
Okay, he's doing
and
three
the main
of them.
loop.
The two threads. Let's see if this is...
Updates the game logic. So you bit 4210, do VRAM, OM, CGRAM, scan the pad, set NMI done flag, and then RTI. And then your main game, you load the NMI done flag, keep looping until it's changed, update your game logic, reset the done flag, and then jump the main game. Note how I set NMI done flag last. This allows you in your NMI routine to check to see if the frame is ready for update. You don't want to update a partial frame. That will lead to glitching. Although you may want to put it partway through the logic, once you have updated all the VRAM mirrors and you are doing other tasks such as updating the music and sound effects, unpacking blocks for further along in the map, which if they spill over don't affect the frame integrity and are safe to be interrupted by the NMI. Personally, I feel the first two on the SNES are fine for quick demos, testing, but not something you should really use on a game. The third method is not really that much harder to deal with and will serve you better in the long run. It does come laden with traps, however, as does everything on the SNES. So let's walk through an example and I'll explain and disarm all of them for you. This is for low ROM. I'll start with the NMI portion of the routine. The NMI will always start in bank 0, so we need to jump long to a fast bank. The JML changes the program bank, but not the data bank, so the data bank is still slow. Also, we don't know what the data bank is. Maybe the code was interrupted has changed it to somewhere else. If the NMI ready flag is in the shared 8K of RAM, it's 99.5% safe. However, if the data bank is set to 7F, it will fail. So, push the data bank to save it, push the program bank, pull it into the data bank so we match.
Oh, okay. So he does talk about the pushing and pulling. Wait, let's see what the. Okay. One watching star. Wait, this thing is still running, isn't it? Yeah, it is. Okay.
Now we want to test the flag to make sure we are safe. So I make sure A is 8 bits. First, however, I act the NMI. If this doesn't happen, we won't get any more VBlank NMIs, which will lock the game up. Note, I use bit. The register just has to be read. And bit has the benefit of not changing any CPU registers. Now we bit the NMI ready flag. Note I put an F on the end, so I know while coding that this is a negative active flag. I also have PF for positive flag, NZ for not 0, and EZ for equal 0. Also notice the @W. This is the 64 task way of forcing 16-bit addresses. It is .W in WLA-DX, and I believe also in CA65. Why do I do this?
Calculator went up.
Because we don't know where the direct page is. You could also make sure the NMI ready NF is not in a direct page variable. However, this way, should it be or not be, we are safe. Now, if it is still negative, we know we have not completed the last frame, and we exit. So we restore the data bank and RTI.
Okay, I just want to say, a couple minutes ago when I saw that he just did the bits for 4210, I was okay. I knew why it was simplified, because if he showed all this crazy ass code, that would just scare people away. But now he's actually showing, okay, this is how it is when you're doing in detail without all the. Whereas the other one was just oversimplifying. Okay, that's the reason why I was trying to figure. My computer's being so slow.
The interrupt system and RTI save and restore the processor status flags as part of their internal operations, so we don't need to save and restore the processor flags, which also includes the size of CPU registers. If we are still on this code, then we are ready to do a VBlank update. Now I need A, X, and Y to be 16 bits for preservation. We save A, X, Y, and then direct page register. We need to load a known value to be safe and ensure the DP accesses actually go where we expect. I'm assuming 0 here, but it can be anywhere, just as long as you know that it is where it should be. Now you are ready to run your update code, DMA OAM, update the tile map, update PPU registers, etc. Now we leave.
By the way, I like the way he just sets up enough so I could just bit test this, but then do the rest over there. I never really thought of it that way.
Bit for setting the flag. I load a negative number. I just chose FF, and and then we store it in NMI ready NF. Now since I have DP at 0, it is safe to do without the @w. If you move it elsewhere, and that elsewhere is not in the DP, you may wish to add the @w. You could also do a dec if you wanted to save 2 bytes, but it will actually be slightly slower than the immediate load store combo. Restore DP, Y, X, and A, so reverse order, the databank, and exit. That is all for this video. In the next video, I'll be looking at how to properly start and boot up the SNES.
Okay, so yeah, that was a pretty interesting video. The first wait. Yeah, I kind of like the way you use like bit testing to do like 4210. Was that the correct? Yeah, like well, when I started programming the Super Nintendo, I always got like confused about which like what I'm supposed to like write at like what register to get the
The SNES is a
NMI
very
working
fancy
correctly.
pile of sand. There is no code or logic in it. Well, there's a small amount of boot code in the SPC 700, which is basically its own little computer, but the main machine has nothing. No BIOS, no kernel, just metal. So this means when the machine is turned on, we have to bring it up. This is the opposite of most other machines. For example, the Game Boy has its own boot ROM, and the Commodore 64 has a complete kernel. It is not unique, however. The NES and Atari VCS also have nothing. For this, we have to take a deep look at the 65816.
Wait a second. Why does it say
the Commodore 64 has a
live capture of NES with cart? What?
Complete kernel. It is not unique, however. The NES and
Okay, I just want to say, like, I don't even think that the original NES had a color
Atari VCS
that's particularly
also
bright.
have nothing.
I mean, especially one that like is able to like smoothly transition from black to red like that. So, I mean, I think if there was like
the Commodore 64 has a complete kernel. It is not unique, however. The NES and Atari VCS also have nothing. For this, we have to
okay with the red being on the NES. I guess it depends on like what like emulator you're using. Some like emulators use like red, but doing it like with like a smooth transition from like black to red would like only be like black, dark red on like on an NES anyway, so there would only be like 3 levels.
Take a deep look at the 65816.
Instead of a smooth
its
transition.
Dual personalities make it rather unique. The 65816 was basically commissioned by Apple to bring the Apple II line up to date by making it 16 bits. For this reason, the 65816 had to support the 6502 and do its best to support the N6502, not the 65C02. For some reason, it was decided it would boot into 6502 mode. This makes sense in that the 6502 code would not know how to switch out of 6502 mode, and hence it would be compatible still. However, it is not pin compatible with the 6502, so I don't see how this case would arise. Perhaps Apple decided to reset into Apple II mode and later abandoned it. Having 2 modes gives the machine some odd properties, such as 2 sets of vectors. The 6502 ones that now start at FFF4, technically, and the new 65816.
Hey, by the way, I think the IRQ interrupt should just be called the mom interrupt, because my mom always interrupts me, like, at random times.
Ones
and I'm expected to just like push everything that I'm doing onto the stack, and then pull all the stuff I'm doing back onto
some of these
my
don't
brain
make sense,
processor.
as the 6502 mode will never get the break interrupt. It still uses IRQ. Technically, the COP should never happen to 6502, but I believe it does work. The 65816 reset vector will never trigger, as when the chip is reset it will drop to 6502 mode. So these are free for you to use as you please if you like. Also, abort will never trigger on a SNES. So what?
Oh yeah, I'm like when I'm programming, I usually like. What the heck? Why is it? The heck? Why is the words on my thing black all of a sudden and blurry? That's weird. This thing's being slow too. Oh yeah, what I was saying is I usually keep this. These addresses and these addresses are the same way because like like it doesn't really make any difference, and there's like it doesn't really make a difference, and like it doesn't.
What happens when reset interrupt fires?
It's like I don't even think they actually needed
0,
that anyway.
Data bank and program bank are also set to 0. Stack high is set to 1 as per the 6502 stack. However, stack low either as it was or in the initial reset case as the solar flare commands. X high and Y high are 0, but the lows are again as the solar flare commands. All of A is as the solar flare commands. The status registers will be in 6502 mode, and negative overflow and 0 flag will be as the solar flare commands. M and X will be 1 to ensure 8-bit A and indexes as per 6502. The BCD flag will be 0 always, unlike the mostly on the 6502. I will be 1 and E will be 1 to ensure 6502 mode. Vector will be pulled from 00FFFC. Don't worry too much about the setup here, it's just for the context and to provide a complete picture. I will be discussing it and giving more complete setup in the next video. Now that we are in our own code, first things first, we want to get into 65816 mode. This is done with a CLC followed by an XCE to move the C flag into the shadowed E flag. This pulls it low. Status flags with the exception of D are active low. Now as this is 2021 and you are not making actual cards anymore, so don't have to pay the extra 50 cents, you want to enter the fast ROM area. So we set the fast flag and then JML to the next address, but in bank 80. This is moved to program bank, but not the data bank. That is still in the 00 and thus slow. But to set the banks, we need the stack. So we set up the stack. Now we can put the stack anywhere. I recommend putting it at 1FFF as you have to break the data flow because of the registers in the shared RAM anyway. In this way you have unbroken RAM below it and then long access above it. The 65XX stack grows down memory.
Okay, I know. When I watched this video before, like something that I've noticed was that, he goes into native mode here, and then like I noticed that he loads number 1 into the accumulator as if it's already in 8-bit mode, and he stores that as if the data page is already 00. Is that is that how it works in default? I always like assumed that it was. I always assumed that it was like it worked like RAM, where the registers are just filled with like random variables. I don't know. I guess maybe I just like.
In this way, you have unbroken RAM below it and then long access.
Like, does he say that?
But to set the banks, we need the stack. So we C followed by an XCE to move the C flag into the shadowed E flag. This pulls it low. Status flags with the exception of D are active low. Now as this is 2021 and you are not making actual cards anymore, so don't have to pay the extra 50 cents, you want to enter the fast ROM area. So we set the fast flag and then JML to the next address.
I know. I need to look
80.
that up because
This is moved the program bank, but not the data bank.
it could be that it's
0,
like
0, and thus
it could be set to like
to set
8-bit
the
mode
banks,
by
we need
default.
the stack. So we set up the stack. Now we can put the stack anywhere. I recommend putting it at 1FFF as you have to break the data flow because of the registers in the shared RAM anyway. In this way you have unbroken RAM below it and then long access above it. The 65XX stack grows down memory. Load X with 1FFF and TXS. Now we have a valid known stack. Push the program bank and pull it into the data bank to set it as fast as well. Now I want to set the DP to 0 to be sure. While it will be 0 on a true reset, we don't know how the user has booted their machine. Could be from an SD card. We also may have done a software reset. So now the CPU is in a known state. Time to set up the rest of the hardware. The PPU has recommended initial setup values, which are listed in Chapter 26 of the Super Nintendo Development Manual Book 1, which I won't show here for obvious reasons. However, first we want to clear our WRAM. But why bother? If you've used a high-level language, you will know the pain of works in debug, but fails in release. Same principle. Your emulator clears it with 0. You use some value, maybe accidentally read a 16-bit value, and the high is 0, so nothing bad happens. But on an actual machine, that memory location is now as the solar flare decreed, and your code crashes. Or they reset at just the wrong moment, and now it's invalid and you crash. Or you test on your flash card and it's the third item, and it just so happens to put the right value in memory location, and your code works. Then somebody else runs it on another card, or it's item 50, and you crash. Why do it first?
Okay, you know, why is he putting, if this is supposed to be, if the data bank is supposed to be 0 by default, why is the data bank 0 by default if the direct page isn't?
We hold important things, such as our stack and our register mirrors. So before we do anything else, we need to clear WRAM. However, first, we will make 100% sure we are in forced blank. This is fairly straightforward DMA, fixed source 1 byte to WRAM port. I have a 0 word somewhere, they are easily defined generally. Here, rather than drop to 8-bit to write the byte, I just write a word because I'm going to fix up the next byte with a write again anyway. I.e., if you write the wrong thing and then write the right thing later, doesn't matter it was wrong. No. Again, I have to write 3 bytes. Just overlap the write. At this point, I've wasted 2 clocks. But to do the 8 bits, 2 and then back to 16 bits would have been 4 clocks. So I'm 2 ahead still. We set the length to 0. This is because the DMA engine decks then checks for 0. So we'll stop on 0. If we start at 0, it will deck to FFFF, then check. So this way we will do all 64K via the DMA. Since the count will be 0, the source is fixed and the port has incremented to the next bank, we can just fire it again and do the upper 64K. You may be tempted to put this into a function. It seems like a nice thing to put in a function. It is not. Stack doesn't live in some ethereal plane. It lives in work RAM. So you'll JSR to it, which saves the return address on the stack. Then you nuke the stack with 0 with the DMA. Then you'll return to 0, which will hold 0, so it will break. It will RTI, then break. RTI.
I like the way he has overlapping overlaps this stores 0 and this stores 0, whereas this stores 0 zeros 81 and 82. This one's zeros, 82 and 83. Yeah, I do something similar to that when I'm like building in my game when I'm building OIM, where the top byte of the X and Y, the top byte of the X coordinate gets overridden by the low byte of the Y coordinate, and the top byte of the Y coordinate get overridden by the attribute word. I do something similar to that.
And break, and so on.
Where I have like overlapping.
Now we can get on with the knitting machine, which could now be placed in a function if you prefer. But before we get to setting them, a couple of points about how the registers work and are laid out. Very few registers are read and write. They are ordered write only,
By the way, I
then
like to point out that I like the idea of like doing two DMA loads like right after another because 0, 0, 0 like wraps around to like 64K length basically, and if you're doing it twice, it just just continues where it left off.
Very few registers are read and write. They are ordered write only, then read only. So the PPU registers from 2100 to 2133 are write only. This means if you try and do an LDA 2100, it will mostly read the last.
Yeah.
She said that there's a form she's gonna send you, and you have to. It's just if you're gonna go to Harvard for not Harvard, for Oakton
Okay.
for one in school class.
Okay.
Okay, you finishing up your work now?
Yes. The reason why I never tell my mom that I'm doing live streaming is just because if she finds out that I'm doing live streaming, she'll just like complain that I'm talking to strangers because she bathes me like that.
21, not the actual value. 2134 to 213F are
Oh yeah, you know, like my mom thinks that when I get angry, when I get nervous, it's always like people bullying me on the internet. She doesn't realize that part of the reason that I get frustrated is that she doesn't believe that I could handle the situation myself. I mean, it doesn't, like, getting bullied on the internet doesn't really happen to me all that often anymore, and I mean, even if there's, like, a risk of me being bullied, it's, I feel like it's, like, the risk is willing to take just because, like, so many people get money from like doing YouTube videos. So like I mean, hopefully, if I could get like enough viewers, I could eventually get some money. But I kind of I'm stuck in this catch-22 problem where like I need to find a way of getting out of this house in order for me to find a way to make money, but at the same time I need to make money to get out of this house. You know what I mean? It's like I don't know. If I lived by myself, I feel like it would be a lot easier to find a job because they don't get interrupted. all the time,
only.
basically.
If you try and write to them, nothing will happen. Only this splits the VRAM, CGRAM, and OAM write and read registers. To write to VRAM, you use 2118, and to read, you use 2139. The 4 APU ports are read and write. The WRAM port at 2180 is, however, read-write. But the address setup 81, 2, and 3 are write only. The CPU on-chip registers, not to be confused with the AXY etc., are also split with 4200 to 4200D being write-only and 42010 to 4001F being read-only. 4016 is read and write, 4017 is read-only. The DMA engine registers are all read-write registers. Now, we can't initialize the read-only registers, so we only need to worry about the write-only registers. The read-write nature is inconvenient. For example, say you want to enable sprites. You don't want to modify the other screen setup, just turn on sprites. Easy enough, we just need to set the 4th bit of 212C. So you load 212C, you hold the bit, you store it back. Can you see what is wrong with this code? 212C is write-only, so when we read it, we will mostly get 21 into A, or 10 with it, and thus store 31 into control. So we will turn on BG1 and sprites, and turn off 2, 3, and 4 if they exist. Not what you want, but as you can imagine, when you start out, you probably only have BG1 on, and when you turn on sprites, so the code will appear to work just fine. Only to fail horribly later when you add a hard on BG3 and spend hours head scratching as to why it used to work, no longer works. To avoid this, you create RAM mirrors of the registers you need. This way, you keep a copy of its last value. This also helps with setting, as you can modify the PPU registers at any time, which is not always what you want. Enabling a screen mid-frame will probably cause an ugly glitch. So you modify the RAM mirror, and then copy the mirrors into the actual registers in the NMI. How many and how often you copy depends heavily on your use cases, so you might make a dirty flag, which is checked and then if dirty does the update. You may also break it down and do multiple dirty flags. For example, you probably don't change the screen mode and the base addresses every frame, so you make a flag to set them when dirty. But
by the way, I like this. Wait, I'm gonna go back a little bit.
You modify the RAM mirror, and then copy the mirrors into the actual registers in the NMI. How many and how often you copy depends heavily on your use cases, so you might make a dirty flag, which is checked and then if dirty does the update. You may also break it down and do multiple dirty flags. For example, you probably don't change the screen mode and the base addresses every frame, so you make a flag to set them when dirty. But
yeah, I like this idea because OZ Phantom has a lot of good ideas. That's something that I've my VBlank code in my homebrew game is very sloppy because there's some registers that I use, some ones that I don't use, so this is a good way of balancing CPU speed during VBlank. Because if you could just have these registers that rarely get used, if any of them gets used, as do the whole thing, because most of the time these are updated at once. You could do it where nitpick of having a dirty flag of each individual register, but that would make it. There's there's no such thing as a perfect engine, but I think that this is a pretty good idea.
Setting the H and V scroll registers is probably something you do often enough to just do it every time, regardless of setting testing flags will cost you more time. There is no need to mirror all of them either. For example, OM address and data write, you will just set these directly every time you want to use them. Windows depends. Typically you get updated in HDMA runs, but if you do have some full height window effects, it might be worth it. Mode 7 registers? Are you doing Mode 7? Yes? 100% mirror. No? Don't bother. The CPU write-only registers are either set and forget, or things you will fully set up and change when needed. So no need to mirror them, except 4200, which can be nice to have mirrored. The DMA ports? No need. What does this look like in code? First thing, 16-bit mode. Most registers are going to be 0, so why waste time and bytes doing it byte by byte? Also, I still have the right mirror code here, commented. This is so you can see what I would have had a mirror for. Most of it doesn't need to be written, as the clear of WRAM cleared them as well. So only values other than 0 need to be written. First up we have initial display. I'm using no caches full SNES naming for these. Best to set it blanking, as we have a lot more setup to do, and set brightness to full, so when you turn it on later, you will actually see something without making that simple mistake. And we clear object select and base at the same time. You might be tempted to optimize this and put your initial values into it. Don't bother. You will need to set up the screen modes again and again, the title screen, the intro, the main game, etc. So it would just be pointless optimization. Onto BG mode mosaic, 0 is fine. The screen bases. So by now you may have noticed two things. One, I am treating the mirror variables as words, as the STZ will write to 2107 and 2108, but then I zero BG1 and BG2. This is something I recommend. I'm not going to go into detail why now, that will probably be a thing for video 4. Short answer is to protect yourself from oops 16-bit mode and I wrote an 8-bit address and trashed something randomly. The second thing you may have noticed is the lowercase m. This is Hungarian notation. Old school machine, old school solutions. Again, video 4. The name bases, now the H and V offsets. These are doozies. They are byte double write with a hidden internal latch. So write only with internal latch. Now you must be very careful with this.
Okay,
If
when
you
I watched
only
this
write
video
once,
before,
then
like,
you will get an
yeah, I'm not exactly sure if this works, cause like, wait, let's.
So write only with internal latch. Now you must be very careful with this. If you only write once, then you will get an odd, and then all future writes will write high-low, not low-high. And you can't tell. You can't.
Okay, no, I'm not exactly sure if that's true. There's like some like there's some debate over how there's some debate over how these like write twice registers actually work. I'll get wiki.cdperhamlet. Okay, this actually worked. Registers. There's like the way it's being explained and on this website is a little bit confusing. Wait, where is it? Yeah, like I wanted to make this like I should have made this a prepared content video because once I started oh yeah. Ooh. Okay. So okay, so let's now that these are write twice registers, first byte is written, then the high. Current theory is that the registers work like this, blah blah blah. Note that there is only one previous shared by. And by the way, I noticed that there's like a when I read this earlier, I noticed that there's like a contradiction. It says note that there's only one previous shared by all 8 blah 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 registers and only one previous to shared by the 4 blah 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 registers. These are not shared with M7 registers, not even this and that. Well, this is a contradiction because if you're not including these registers, it should only be like 6 and 3. But anyway, like I find okay, so from the way this, like, I had to really, like, study this, like, for a while, because, like, it looks like gibberish. I figured out that the and 7 is supposed to mean it's, like only, like, the first 3 bits, and this is, like, everything but the, and not 7 is supposed to be, like, everything but the first 3 bits. So apparently, well, let's try to figure this out. In Microsoft Paint. What resolution is this in? I don't know. It doesn't say what the resolution. It usually says what the resolution is. I guess maybe because it's going slow, it's not. Okay, so apparently there's the red. Okay, there's. Okay, so I'll call this one. Ooh, like, come on, computer, what the heck are you doing? What the heck is this crap? Nothing? Why am I getting, like, nothing? No words or anything? Wait. I'm just getting, everything's blank. I don't know what happened. I guess I'll just have to doodle in the words automatically. Let's say background X H. Wait, I should do how am I supposed to explain this? These things. Maybe I'll do a prepared content video because it's just not working. This is. My computer is, like, giving me a hard time. Okay, so because they're like. Okay, so basically. Okay, this is supposed to be one register. This is supposed to be. Why is my. It's not. So. Oh yeah, I forgot I could do this too. So apparently there's like 2 extra registers that are shared, and I'll call this one. I'll call this one X high. X low. Y high and so apparently the way it's supposed to work, the way it works according to superfamicom.org, is that whenever you write to a register, this goes into. Wait, is this how it works, or is it the other way around? No, wait. I should say that. Okay, wait, I think I'll do P1 and P2 just so. P2. So what happens if you write to this? If you write to this register right here, the current one would go into here. The thing being written would go here, here, and here, whereas this right here would somehow like be a combination where like yeah, for some reason the first 3 bits come from this register, whereas these 7 bits come from this register. But if you're doing it, if you're like, I'm going to use a different color. Let's say, but if you're writing with this one instead, this just goes here, this goes wait, should do it. This goes here, and this also goes here. Now, what's even more confusing is that if you actually go on click on backgrounds, let's see. Wait, I think I'll do like a pattern here. So like, I think I'll color this in yellow because this is supposed to be like if you click on this side, it contradicts itself again, whereas according to the background pages, this instead of P2 being its own register, it instead let's get rid of P2. It instead borrows the first 3 bits from this other one, apparently. I don't. Yeah, it's weird. Yeah, it's weird how they did it. Like, yeah, it's weird how they did it this way. It's like maybe the reason this was done like that is because maybe like originally the Super Nintendo was able to maybe originally the Super Nintendo was able to have like a backgrounds that are 2048 pixels wide and maybe this part of the register doesn't actually exist, and like this register is only actually like 3 bits, and they were able to like switch these bits over here, and they use this as like a shared register for all of them, and they were able to like store like the other 7 bits like in here. But the question is, why 3 bits if I can't think of a single mode that actually uses that? I can't think of a single mode that uses more than like 1024 pixels. I don't know, maybe like I don't know, maybe it has something to do with mode 7, I guess. I don't know. And I wonder why these, like, the Y registers, like, work differently than the X registers. But anyway, like, I mean, assuming both, like, either way, it's, like, at first I thought that, what? Whereas, okay. At first I thought that this wouldn't work because it's like, all of them are using like a shared register and it, gets all like funny, but like, the way it's described on Super Famicom, I realized that it would work both ways because, like, either way, because, uh, like the previous byte would be zero anyway, so it's just, like, okay, if I explain more, my tongue will get even more tied. Like, that's the problem I have. I have a hard time explaining things because my tongue gets tied explaining things. So
read from it to work out if you're reading high or low, and you can't read the internal latch. And
like, I'm not exactly sure if this would actually work. But I mean, the way it seems like how it's described on Super Famicom, it seems like it would. Okay.
there is no reset to latch, to be sure. So always write to it twice. Be very careful when you're writing to them to make sure that you are 8 bits normally. In this case, I want to set both H and V to 0, so it's fine. And also be very careful when you write to 210C, because that is a byte. And if you accidentally write a word, then BG1 horizontal is going to become odd. So always modify the mirrors. And make sure you write the code to write the mirrors very carefully. And never write the registers outside of your perfect, thrice-checked code. Mode 7. If you're doing Mode 7 work, add some mirrors as well. Again, these are double write registers. Onto the Windows. I have mirrors just in case. I do double writes. It's faster than switching to 8 bits, then switch back, as we need to do a special odd write up ahead and an odd number. It was just cleaner here. The object mirror, the main and sub screen designations, disable the windows, and I set the color maps to be 0 on RGB so it doesn't do anything too bad should it become active, and clear the display control too. Now onto the CPU I/O registers. We set the controller port out to FF. Most things are active low, so this is off. And we set the VBlank enable to off. A mirror for VBlank is nice. Then we just clear the rest, no need the mirror. So we have the CPU and the PPU in a known, stable state. We are not done yet. We still have VRAM, CGRAM, and OAM. Why VRAM? A classic bug is accidentally enabling screen 3, but your VRAM is all 0 so you don't see anything. Then flashcard or reset leaves stuff in the VRAM and suddenly your title screen has random garbage all over it. For this, we will again DMA, a fixed value of 0. For this one, we want to write a fixed word to registers 18 and 19. We shouldn't technically need to set up the address again, but it doesn't hurt. Again, size is 0, as we want to do 64K, start at 0, and fire. Now, CGRAM. Fixed source, write a byte to address 22. We only need to do 512 bytes. Start at 0. I have to drop to 8 bits because 2122 is not safe to write to, and since 420B is a byte register, I stay 8 bits for the file. For OAM, you don't want to set it all to 0. You want to set all sprites to be off screen and small. Since this is a common action, you will want to do multiple times, and you will have an OAM mirror, and you will constantly DMA OAM to VBlanks. We won't do this with custom code, but with main engine functions. This is a topic for another video. I hope you have learned something, and will join me for the next video where I'll go over the weird dual address systems of SNES space and ROM space, and how to fully set up and build a card image.
Oh, and by the way, I didn't catch it this time, but when I first saw the video, I noticed
to
I noticed some of the numbers being wrong somewhere. But wait, where is it? I mean, I noticed that. I think that's
nice thing to put in a function. It is not. Stack doesn't live in some.
okay. was it here? Okay, the numbers seem to be...
no longer works. To avoid this, you create RAM mirrors of the registers you need. This way you code and the base addresses every frame, so you make a flag.
Aha! Here's like, yeah, I noticed that. Like, I noticed that this should be like 21.0A, not 21A. And same thing with this. This should be 21.0B instead of 20.01B.
Like to set them when dirty. But setting the H and V scroll registers is probably something you do often enough to just do it every time.
Yeah,
regardless of setting
I
testing flags will cost you more time.
The first time I watched through this. So, okay, so... Yeah, so about this one, the only thing is that, like, I don't know if writing to the fast ROM register, like, in an 8-bit mode, like, without setting anything else up first actually works. So, like, I don't know about that, and I don't know, and the register numbers, like, are typed in slightly wrong, which I explained there. All PPU registers are 21 something something. So, and the talk about the I'm not exactly sure how the write twice registers work. So, I mean, it could possibly
Sell
work if
online
you're
and grow
doing
your
like zeros, but I just...
The
like, if you're unsure, then you could probably ask people on nesdev.com, and like, if you just want to make sure it works, like, make sure it works without asking anybody else, you could just do it the normal write twice in like 8 bits. So anyway, so I think that's like my review. Has this guy made like a part 3 yet? No, just... Okay. Oh, he has like oh cool, he has a video of just regular like 6502 programming, so it's pretty interesting. Can you make Super Mario Bros. Huh, that looks interesting. You know, I think some of this other stuff I would like to like watch, like, but like, I don't know, this like video is like this video is kind of like crappy because my computer is being slow, yada yada yada. So that's it. Click the subscribe button if you want to see more videos like this. Bye everyone. Oh boy. Oh boy. It's okay. Wait. Hold on. Yeah, I'm still having technical difficulties. I should have made this a prepared content video instead of a live stream. Oh boy.